the new section we want to talk about it next is the section 2.4, arc length of a curve. So in this section, we are going to talk about both arc length and the surface area. So you are going to see multiple videos. The first one here, what we want to do is just introduce what is arc length. So imagine that if I have 2 points on any xy plane, it is easy for me to find the distance between those 2 points by building a right triangle, either using the distance formula or Pythagorean theorem. We can find the distance here. This is the difference in terms of the x. This is the difference in terms of the y. So the distance is going to be the square root of the distance in terms of x squared plus the distance in terms of the y squared. So this is the distance formula or the Pythagorean theorem. So either way you want to think about it, but it's the same formula. So now we want to use this concept to find the length of a curve. So imagine that this point is not just 2 points. This 2 point is coming from the piece of arc. Then I cannot really find the actual curve of this purple one, but I can using this straight black line to approximate the distance of this purple arc length. Now, if this is a zoom in of a larger graph, then what we can do for this larger graph is, normally the larger graph are placed on the xy plane. And what we can do is we can slice this curve into different slices. And then for each slices, we can thinking about, we will have those starting and then the end points on the curve. And for each piece, we're going to using this concept to approximate it. So eventually, we were going to slice the curve really, really thin. So eventually, the thin curve, the approximation will be pretty much the same as the actual curve. So what is that? That is a limit. That is the limit of slicing this curve into really, really thin, slice. So by combining everything we just talked about it, the arc length is going to be a limit where I'm going to taking the limit that the delta x is going to be 0, which is this one is going to be approaching to 0, of a summation of those distance. Now this is not really a precise way to derive the formulas, but this is what actually we're doing here. So when I have a long piece of graph, I want to find the actual arc length. What I do is I'm going to slice this one into infinitely multiple slices. Then for each one, I'm going to zoom in to find the approximate straight distance from the beginning and then the end point using the distance formula. But this is not something we know how to do it. So we're going to using some algebra to simplify it. So what I can do is I can divide or factor out the square root, the difference x, delta x squared. Then inside is going to be dividing 1 plus delta y over delta x squared. We can put this one out to get the limit summation delta x square root of 1 plus delta y over delta x squared. So what is this limit as delta x approaching to 0 of delta x? You are thinking about that one probably going to be equal to 0, but it's not. It's going to tell us that it's going to be a really, really thin slice. It's going to be getting really close to 0, but not 0. And we're using a special symbol to determine that, which is dx. So the limit delta x approaching to 0 of delta x is going to be rewrite as dx. Then for the same thing, the limit delta x approaching to 0 of delta y over delta x is going to be rewrite as dy over dx. Now, what is dy over dx? This is just going to be the derivative, the first derivative. So by combining everything, the actual formula for the arc length of any function f is going to be the integral from a to b, because we're talking about a segment. We cannot talking about the length of a line, because the line will keep going and going. The segment has a starting point, has the end point. That is something we can measure. Square root of 1 plus the first derivative of the function square dx. And that is going to be the formula we will use for the arc length.